You know, human imagination is absolutely boundless, but translating those wild, abstract ideas into physical reality, well, that requires a highly structured, absolute language. Welcome to This Explainer, where we're going to dive right into exactly how that happens.
I want you to picture a complex architectural structure in your mind right now. Maybe it's a towering skyscraper or a perfectly engineered suspension bridge. Now ask yourself, how could you possibly communicate that perfectly to a team of hundreds of builders, fabricators, and engineers? You definitely can't just describe it with words. Words leave way too much room for interpretation. You need a method that is absolute and completely precise. And that's where the physical tools of this translation come in. We're talking about calipers for exact measurement, drafting pencils, precise bearings. These aren't just random objects sitting on a desk. They are literally the instruments used to bridge the gap between a floating idea in someone's head and a concrete, measurable object in the real world.
So, before we get too deep, let's quickly run through our core learning outcomes for this unit. We're going to explain the function of engineering drawing, identify its core elements, figure out why standardization is so incredibly important, and identify the actual drawing equipment and materials used.
To do all that, our agenda is pretty straightforward. We'll cover from idea to construction, the power of visualization, communicating across the industry, and finally, documenting for the future.
All right, let's jump straight into Section 1, from idea to construction.
At its core, drawing serves as a vital bridge. Its absolute main purpose is transferring information from an abstract thought into a highly specific, totally understandable display. It takes the invisible and, quite literally, makes it visible. Without this bridge, your ideas are just going to remain forever trapped in your mind.
This creates a really clean, predictable, three-step pipeline that basically governs the entire engineering world. Step 1 is the idea and design, that initial spark of innovation. Step 2 is the drawing, which is the translation phase. And Step 3 is construction, the actual physical realization of your design. And trust me, you simply cannot jump from Step 1 directly to Step 3 without courting absolute disaster.
It's a fascinating flow. We start with that light bulb moment. That spark is then carefully filtered through drafting, where it becomes standardized, usable data. Finally, that data flows out into the real world, resulting in a finished, constructed building or product. It's a continuous, unyielding flow of information.
Moving right along to Section 2, the power of visualization.
Visualization really is the magical first step. It's the method of extracting the fruit of your mind and placing it into a shared physical space so that everyone else can see it. It completely removes the guesswork. You aren't just telling someone what a part looks like, you are showing them its exact geometry, its precise dimensions, and exactly how it relates to every other part.
But here's the real kicker. The ultimate benchmark of success here isn't just drawing a pretty picture. The person looking at the drawing has to understand it so completely that they could actually draw back exactly what they see. That flawless replication of the original creator's mental image, that is the true test of visualization.
Which brings us to Section 3, communicating across the industry. You see, communication in this context isn't just about handing someone a piece of paper. It's about conveying ideas through a specific graphical language that guarantees any engineer, totally regardless of their native spoken language or background, can decode the exact same message. Engineering drawing is truly the global language of the technical world.
So how do we actually ensure everyone understands this visual language the exact same way? Well, to avoid absolute chaos and misinterpretation on a busy job site or a manufacturing floor, all of these drawings must strictly be drawn to a certain standard. Every line weight, every symbol, every single dimensioning practice is agreed upon beforehand. This standardization is exactly what turns a mere sketch into a legal, actionable engineering document.
And finally, Section 4, documenting for the future.
This is the meticulous archiving phase. Documentation is the careful collection and arrangement of all those standardized drawings into a secure, permanent record. It stores every single piece of information, every tolerance, and every material specification. It serves as the absolute, undeniable basis for the production of any product.
And why does this matter so much? It's simple, really. These records become the essential, unchangeable reference for all future production and any subsequent iterations. Think about it. If a machine breaks down 50 years from now, engineers aren't going to just guess how to fix it. They pull the original documentation.
It effectively acts as the historical memory of the entire engineering world. So, when we pull this whole thing together, we see a beautifully logical system. By utilizing visualization to form the idea, standardizing our communication to share that idea without a single error, and rigorously relying on documentation to preserve the idea forever, we truly master the complete language of creation. These three pillars literally carry the entire weight of modern engineering.
I'll leave you with this final thought to ponder. Look at the structures, the technology, and the transportation systems around you today. Which of these human marvels would have been utterly impossible to build without this exact, universally translated language? The answer, of course, is absolutely all of them.